And now I understand that Lenore is going to be joining us with her presentation. Are you there, Lenore?
I am here.
Excellent. All right, you are good to go.
Okay, thank you. I'm going to talk about the hydric soil technical standard, and a lot of what was discussed earlier today is incorporated into the technical standard. The hydric soil technical standard and data submission requirements for field indicators of hydric soils is actually a hydric soil technical note that the National Technical Committee for Hydric Soils has produced. Jacob Barkowitz and Chris Noble recently updated the technical note, so if you've looked at the technical note in the past and you haven't been to the website in about 8 months or so, you may not have seen the most recent tech note on the technical standard. We did not change a whole lot, but we just put it in a format that I think is more user-friendly. All the information in this presentation and all the examples in this presentation are actually in the technical note. I'm going to go through a lot of information very quickly, so if you can't process it all right now, you can actually go to the National Technical Committee's website and look at the technical note, and everything that I'm going to go through today is in that tech note as well. Okay, the purpose of technical standard. It is basically just another means of identifying soils that meet the definition of a hydric soil. Very similar to the field indicators of hydric soils, it is a proof positive way of identifying that you meet the definition, meaning that if you meet the technical standard, it is a hydric soil. If you don't meet the technical standard, there are reasons why it may still be a hydric soil, and I'll get into those in a little bit. So the purpose is to identify hydric soils when a field indicator may not be present. Obviously, it's easier to identify hydric soil out in the field if a field indicator is present, because you only need to go out there one time and identify it as hydric soil. But if you can't do that, this is a quantitative way of identifying that soil as hydric. The reason a field indicator may not be present is maybe it's a problem soil. Problem soils are soils that are hydric, but they lack an indicator because of some characteristic in the soil that suppresses the field indicators from forming. Also, you could have wetland restoration sites or creation sites or just young soils on a floodplain where these soils have not had enough time to develop field indicators of hydric soils. So you may need to use the technical standard to identify it as hydric. You can also use the technical standard to evaluate the current functional hydric soil status of a soil. That is the reason why we can't identify all hydric soils. One reason the technical standard actually measures that your soils are saturated and anaerobic, and in the definition, it's soils that formed under those conditions. They may not be forming today under those conditions, so the technical standard will tell you whether they're forming today under those conditions, but you may have hydric soils that formed in the past under those conditions that will not meet the technical standard. And you can also use the technical standard to propose additions or changes to existing hydric soil indicators. Okay, I'm going to go through the hydric soil definition once again. A hydric soil is a soil that formed under conditions of saturation, flooding, or ponding long enough during the growing season to develop anaerobic conditions in the upper part. Keep that definition in mind as I go through the requirements of the technical standard. Okay, so the technical standard requires that you actually measure that the soil is going anaerobic, and there are 3 methods for measuring anaerobic conditions. One is the indicator of reduction in soils tubes, or iris tubes. The second method is oxidation reduction potential measurements using platinum electrodes, where you're actually using direct measurements of EH potential in the soil. And then the third method is the use of alpha-alpha dipyridyl dye, and there are actually 2 forms of the dye. One is a liquid dye, and the other one is a test strip, very similar to like a litmus paper test strip, and I'll show you pictures of those later. Okay, so iris tubes. If you choose to use iris tubes to identify that your soil is going anaerobic, these are PVC pipes that are painted with an iron oxide coat. You stick them in the ground, and basically, as the redox processes go on, you create a redox depletion on the tube if the soils are going anaerobic. The iron is actually removed from the tube. You can see in the picture on the left-hand side, these iris tubes were in a wetland, and you can see all the paint has been removed from the tube. On the right-hand side, these tubes were placed in an upland, and you will get microsites where you get anaerobic conditions, but you will not get very much paint removal from the tube. If you choose to use iris tubes, you need 5 tubes. You can purchase them There are companies that sell them commercially. You can also acquire the recipe for the paint and make them yourself. And you need a minimum of 5 tubes per site, and 3 of those 5 tubes must have 30% iron removed from a zone 15 centimeters or more thick, and the zone of removal must begin within 15 centimeters of the soil surface, regardless of soil texture. The nice thing about iris tubes is you can put them in before the water tables come up and then take them out when the water tables drop. All the other methods of proving that you have anaerobic conditions in the soil, you actually have to go out weekly to take measurements so that you can show that anaerobic conditions are occurring over a 14-day period. Okay, the second method of proving that you have anaerobic conditions are to do direct measurements of EH. In this case, you need platinum electrodes and a reference electrode, and you once again need 5 electrodes per site. The electrodes you can make or you can purchase commercially. They are fairly expensive, and like I said, you need at least 5 per site, and you need a minimum of 3 out of the 5 platinum electrodes to have an EH measurement that meets the anaerobic conditions threshold, and that actually changes with pH. It has to be less than 105 millivolts at a pH of 7, but it does change with pH. So you also have to measure pH when you're measuring EH. This graph here shows the EH threshold for anaerobic conditions. Along the bottom is pH, and you can see as pH increases, EH has to be much lower in order for anaerobic conditions to occur. When you're measuring EH, your platinum electrode installation should be at 12.5 centimeters in sandy textured soil, 10 centimeters in soils that are flooded or ponded and typically do not saturated. So these are soils that are hydric because they pond at the surface, but they don't saturate from groundwater. And then for all other soils, you would want to put your platinum electrodes at 25 centimeters. And this you need to meet that threshold for 14 consecutive days, so you would need to go out once a week and have 3 measurements in a row that meet the anaerobic conditions threshold to say that you have anaerobic conditions in the soil. The last method for measuring anaerobic conditions is the use of alpha-alpha dipyridyl dye. The dye is a clear dye that when you put it on the soil and you have reduced iron in solution, it will turn pink or red in color. And you need a positive reaction that occurs over 60% of the soil surface that you apply the alpha-alpha to. And you need to test 3 samples, and at least 2 of those 3 samples must meet that 60% criteria. The picture here shows you using the actual dye. And then this next picture shows the alpha-alpha dipyridyl strips. The strips are paper strips. You can acquire them commercially. You lay them on the saturated soil, and either the strips will change ink, or often the alpha-alpha dipyridyl dye will actually get on the soil itself. And you can see in this picture here, the soil actually shows the reddish color too of the alpha-alpha changing color. The reaction must occur within a 5 centimeter layer in the upper 10 centimeters in soils that inundate but don't saturate, so your ponded soils that don't have groundwater. It needs to be a 6.25 centimeter layer in the upper centimeters in a sandy textured soil, and then 10 centimeters of the upper 30 centimeters in all other soils. Okay, so those are the 3 methods you can use to prove that you meet the anaerobic conditions part of the definition. Then you also have to prove that you meet the saturated conditions part of the definition as well. So saturation measurements are taken at 25 centimeters, and it has to be saturated for 14 consecutive days. And you measure that using shallow piezometers or wells. The only difference is if you're in vertisols in Louisiana and Texas, the saturation criteria, you need at least 7 consecutive days of saturation and 18 cumulative days of saturation. Once again, when you're measuring the saturated conditions, you want to go out weekly, and then you'd need at least 3 measurements in a row to meet the 25 centimeter requirement to say that that was saturated for 14 consecutive days. You also need on-site precipitation data. And this is to evaluate whether you're in a normal precipitation year, a wetter than normal precipitation year, or a drier than normal precipitation year, because we're trying to prove that you are going to meet the definition of a hydric soil in a normal precipitation year. Okay, when you're using the technical standard, we recommend that you should utilize data collected at a paired hydric, non-hydric location. So you want to put equipment in an area that you think is a hydric soil, and then you want to put equipment in an area where you think it's not a hydric soil. And you want them fairly close together, because we want you to demonstrate that hydric conditions exist where the hydric soil occurs, and somewhere in between there's a line, and outside that line, the hydric soil conditions do not occur. So if you are using the technical standard to create a new field indicator for soils that have similar conditions and currently don't have a field indicator, we do require replicates, and we want at least a minimum of 3 paired hydric, non-hydric study areas at different locations. And that's so we know that this condition is replicated in different places. If you just want to determine that the soil is hydric on a specific site, then you only need to monitor that site. The data requirements at each location that you're monitoring, you want to write a soil description. Then you need to collect the data to show evidence that the soils meet or fail the hydric soil technical standard. And then you also need to do an analysis of the rainfall normality to tell us whether it was a dry year, a normal year, or a wet year. Okay, the soil description, you just need to write a soil description just like you would do for a wetland determination. You can use the wetland determination forms to write your soil description. However, in the remarks, if there's any physical attribute in the soil that isn't included in other field indicators and currently isn't on the form, you want to make sure you put that in the remarks if that's something you're going to use to identify whether it's hydric or not. But otherwise, you can just write a soil description on those forms. This slide shows examples of an actual site that they used in Michigan to create a new field indicator, and the table shows the upper soil description is the hydric description, and the lower description is the non-hydric description. They both have high chroma colors. They don't have your typical chromas of 2 or less, and the only difference was you did have some redox concentrations in the hydric soil versus the non-hydric soil. It is nice to get photographs of the site, both landscape photographs and soil profiles photographs, whether you dig a pit or whether you use a spade slice. It's always nice to have those photographs. This, once again, is the example in Michigan, and you can see, although there's lots of redox features deeper in the soil profile, up at the surface, they are very subtle and much harder to see. To meet the technical standard, the anaerobic conditions and the soil saturation have to occur for 14 consecutive days. For all the measurements, we require you to at least go out once a week. And like I said, you have to have 3 consecutive weeks where you meet the technical standard in order to say that site has passed that part of the technical standard. The only exception is the iris tubes, where you can actually leave them in until the water tables drop. This example, once again, is from that Michigan site, and this is showing that the site that meets the hydric soil technical standard has soil saturation above 10 inches or 25 centimeters for 25 days, and the one that does not meet the hydric soil technical standard is saturated above 10 inches or 25 centimeters, but it does not stay saturated for at least 14 consecutive days. You do need to meet both the anaerobic conditions and the soil saturation to meet the hydric soil technical standard. So you can't just meet one, you have to meet both. So you need an iris tube evaluation if you're using the iris tubes. In the tech note, there is actually this diagram on the left to give you an idea of what 30% of removal in a 15 centimeter zone would look like if it's just one zone of removal or multiple zones of removal. And then on the right-hand side is a picture that shows the first 2 iris tubes don't have 30% removal, and then the 3 on the right-hand side do have 30% removal. And they're both of those diagrams are in the tech note, so you can use those as a guide. And then this table here is just showing how you can present the data. And in this case here, we once again have on the top, it's the hydric site. On the bottom, it's the non-hydric site. You have 5 tubes, so there's 5 rows. This tells you the installation date, the removal date, the number of days iris tubes were in, the percent removal of the paint, where that removal occurred on the iris tube length. Then there's a column that just says, was there greater than 30% removal or was there not? And then there's a yes or no. And you can see in the hydric case, 3 out of the 5 tubes had 30% removal. And in the non-hydric case, none of them had 30% removal. So the hydric soil passed based on iris tubes, didn't pass in the upland site. Okay, with alpha-alpha dipyridyl dye, once again, we have this table, and in this case, it actually includes iris tube information and alpha-alpha information. We have 3 sites. The first hydric site, 4 out of 5 iris tubes had 30% removal, and it also passed alpha-alpha. Then the consecutive days of saturation, you also had more than 14 consecutive days, so it passed anaerobic conditions, it passed saturated conditions, so yes, it passed the technical standard. The second row is a non-hydric site. In that case, 1 out of 5 iris tubes met the 30% removal. It didn't have a positive reaction to alpha-alpha. It only had 5 consecutive days of saturation, so it did not meet the anaerobic conditions part of the technical standard, nor did it meet the saturated conditions part of the technical standard, so it didn't meet the technical standard. If you go down to non-hydric site 2, you can see 2 out of 5 iris tubes met the 30% removal. It did not have a positive reaction to alpha-alpha. It had 15 consecutive days of saturation, however, so it met the saturation criteria, but it did not meet the anaerobic conditions criteria. So even though it met the saturation criteria, it does not meet the technical standard because it doesn't meet the anaerobic conditions part of the technical standard. Okay, and if you have direct measurements of EH, this graph here shows at the bottom is days, and along the left-hand side is the redox potential, and the dashed line shows you what the redox potential threshold is for the pH at the time that that reading was made. And if you look at the blue squares, they all remain above that threshold, so they stay aerobic the whole time the measurements are being taken. However, the red triangles, you can see, stay above the EH line up until about the second week in January, and then they fall below that EH line and remain below that EH line through March 7th. So the site with the triangles meets the anaerobic conditions part of the technical standard, and the blue squares do not. Here, once again, we show the data in a table format. In this case, the non-wetland is the first 5 rows, and then the hydric soil is the last 5 rows. You need 5 electrodes, so each row represents a different electrode. The column reading in millivolts shows you what the reading is on the actual voltmeter. You do have to adjust that reading depending on what type of reference electrode you're using. So the adjusted or corrected millivolts is there. It shows the pH and then the calculated anaerobic conditions requirement based on that pH. And you can see that none of the electrodes in the non-hydric soil met the threshold, and 3 out of 5 of the electrodes in the hydric soil met the threshold. And as I said earlier, you do also need on-site precipitation data, and that's so we know that you're giving us readings that we can actually use to say that it would meet the technical standard in a normal precipitation year. And we like you to evaluate the 3 months prior to the actual readings to determine whether or not you're in a normal precipitation year. There are some exceptions. Some wetlands that get fed by snowmelt, and in that case, maybe you need to do a different evaluation method. But in most cases, the 3 months prior evaluation method is the method that's going to work to determine whether you're in a normal precipitation year. So in order to do that, you need to obtain the 30th and 70th percentile precipitation data from the NRCS WETS tables. And you can get those if you contact NRCS. They can tell you how to obtain the WETS tables for your local weather station. You need to document monthly on-site rainfall measurements using that on-site rainfall information that you've collected. And when you use that monthly rainfall to evaluate whether you are within the 30th and 70th percentile, if it's drier than normal, you're going to give it a 1. If it's normal, you give it a 2. And if it's wetter than normal, you're going to give it a 3. And it's also weighted by month, depending on if you're in the month closest to when you took your measurements versus the month farthest from when you took your measurements. Let me just show you the analysis sheet. It's probably easier to explain this way. So here, if you look at this first rainfall evaluation from Baldwin County, the measurement was taken in December. So we have the information from September, October, and November, which are the 3 months prior. You've got the WETS 30th percentile number and the WETS 70th percentile number. So in September, it was the 30th percentile was 2.89. The 70th percentile was 7.04. The measured rainfall on site was 5.01, so that's in between the 30th and 70th, so that was a normal condition. October, once again, you got 1.08, 3.74, and it was 3.2, so it's normal. But then in November, it was 3.24 for 30th percentile, 6.25 for 70th percentile, and the measured rainfall was 0.89, so it was a dry year. So the condition value, if you remember, dry was 1, normal was 2, and wet was 3. So the condition value for normal would be 2. The dry condition value is 1. And then the month weight for September, which was the furthest month away from the measurements, was 1. October was 2, and November was 3. So you're going to multiply the condition value by the month weight. So here we get for September 2, for October 4, and then for November we get a 3. You add those together and you get 9. And then if we go back to the previous slide, 6 to 9 was dry. So for that reading, you're actually in a dry period. And then the next measurement that we took was in January, and in that case, we had a wet, a dry, and a wet condition, and that, once you did all the calculations, came out to normal. So you need to evaluate the 3 months prior to figure out if you were in a dry, normal, or wet year. The reason that we make you evaluate the rainfall is because that tells us whether or not the data is reliable. If the hydric soil technical standard is met during a wetter than normal period, you must extend the study for another year. Because if we're saying it's met in a wetter than normal period, we don't know if it's going to meet the standard during a normal year. Same thing, if the hydric soil technical standard is not met during a drier than normal period, then you need to extend your study. Once again, because if it's not met, we don't know if it's because it's a drier year or whether or not it's going to meet it during a normal precipitation year. Any other time, you only need to monitor for the hydric soil technical standard for 1 year. Okay, so in summary, the hydric soil technical standard provides a quantitative method for evaluating whether a soil meets the definition of a hydric soil through the evaluation of the occurrence of saturated and anaerobic conditions under normal precipitation. The hydric soil technical standard will not identify hydric soils that formed under conditions of saturation, ponding, or flooding, but no longer exhibit these characteristics due to hydrologic alteration. So the technical standard is proof positive in being able to say that, yes, this soil meets the definition of a hydric soil. But if the soil meets a field indicator and the hydrology has been altered and it's no longer functioning, then the hydric soil technical standard is not going to work on those soils to identify them as hydric. And the hydric soil tech standard can be used to identify young hydric soils or problematic hydric soils where field indicators are not present, to evaluate the functional hydric soil status, or with replicates, it can be used to propose changes to existing field indicators or additional indicators. And if you've never been to the National Technical Committee for Hydric Soils website, this is the website address right here. And if you look up Tech Note 11, all the information discussed earlier today is incorporated in that Tech Note.
Excellent, Lenore. A superb presentation. And I am just going to pull up my slide for a moment.